Hey, it's Randy. What if there is a modeling problem where part of the question describes time using seconds, and then another part of the question describes time using minutes? How do we solve a problem like that? Let's talk about it. So we are told that the following equation models the behavior of a ball's horizontal velocity, this time in centimeters per minute, in relationship to time in minutes. Now we change from minutes to seconds. Every 45 seconds, what percent of its horizontal velocity does the ball lose? And we need to round our answer to the nearest percent. Okay, let's talk about this. Now this same kind of dilemma that we see with the units, that is, minutes versus seconds, is the type of dilemma that we would see in physics. So how do we approach this? First of all, the beginning of this question tells us that our equation is talking about time in minutes. So this t right here is in minutes. Now all of a sudden they say every 45 seconds, what percent of its horizontal velocity does the ball lose? Now the key to interpreting this problem correctly and answering it correctly is to keep our language consistent, okay? So if we started in minutes, then we need to convert this part of the question, the 45 seconds, also into minutes. So ask yourself the question and try to figure this out. How many minutes is 45 seconds? It's not that difficult. So we know that there are 60 seconds in 1 minute, right? So if we're talking about the 45 seconds, we know that this will be less than 1 because 45 is less than 60. So hopefully you're thinking this, that 45 seconds is the same as saying 45 over 60 minutes. And in this case, 45 over 60 can be simplified. That's the same as saying 0.75 or 3 over 4. So now, in your mind, I want you to replace this right here, the 45 seconds, with 3 over 4 minutes, or 0.75 minutes. All right, look at that. Now we have achieved making our language consistent because they said that the following equation involves minutes, right? They said that the time is in minutes. And now the question that they ask us when they say every 45 seconds, we can now think of it as every 0.75 minutes, what percent of its horizontal velocity does the ball lose? Now this looks like a problem that we've done before. If you look at the video Interpret Change in Exponential Models, you'll be able to see how we solve these problems again. Even if you don't go back and watch that, I'll just tell you that the way we solve this is by plugging in this time frame, 0.75 minutes for t, and then we find the value of that part of the expression that has the variable, which we call b to the power of f of t. So let's do that, and then we will convert the factor that we get into a percent change. All right, there it is. Our 0.75 is now in the exponent in place of t. And so what do you get when you simplify 0.73 to the power of 0.75? All right, here's approximately what we get, and this decimal keeps going. And just like we discussed in the video Interpret Change in Exponential Models, this can be converted to a percent, and this is going to be a percent decrease, right? The velocity of the ball is going down. How do we know it's a decrease? It's because this number is less than 1. So just like we learned in that video, we need to find the distance between this number and 1 and then multiply by 100, and that will give us our percent change. So let's work that out right up here to the right. So if we imagine a number line with 0 right here and 1 right here, where would our decimal be? Well, it's going to be more than 0.5. Here's 0.5. So this right here is going to be about right there. So now we need to ask the question, what is the distance between that decimal and 1? So in this case, we can just say 1 minus 0.78975, and we get that distance is 0.210245. Now let's multiply this right here by 100. And when we move that decimal to the right 2 places, that is multiply by 100, we get a decrease of 21.0245%. Rounded to the nearest percent is 21. So when they say every 45 seconds, what percent of its horizontal velocity does the ball lose? We now know that it loses 21% of that velocity every 45 seconds. Or we could say that there is a 21% decrease every 45 seconds in its velocity. So there it is. All we did is convert all our units for time. In this case, we had to convert the 45 seconds into the units that they said the original equation uses. In this case, the t was in minutes. So we converted 45 seconds into 0.75 minutes. Then we plugged in that value for t and then simplified to find the value of b to the power of f of t. And then finally, we converted to a percent. All right, now real quick, let's do another example, except this time we don't have to worry about the hassle of converting to a percent. So here we go. The total number of branches n of t on a certain tree in relationship to elapsed time, t in years, okay, years is the units for t, time, since the tree was planted is modeled below. Here is the model. Now, every month, okay, so the units changed from years to months. The number of branches grows by a factor of how much? Now, if you remember, hopefully you do, that when we say by a factor of how much, that is much easier to find than the percent because there's no hassle of conversion at that point. We just find the value of b to the power of f of t, and that is the factor that we're talking about. And this time we need to round to the nearest 2 decimal places. So first things first, let's convert these units, months, into years, and then we'll have all of the same units, that is years. So we'll be speaking the same language throughout the whole problem. So the way I think about it is a month, right? We're saying every 1 month. A month is how much of a year? It is 1/12 of a year. So if we replace month with every 1/12 of a year, so we can say 1/12 years. Now we have the same units. We have years right here and years up here. So every 1/12 of a year is going to be what we put in for t. So let's put in 1/12 right there and then simplify. All right, so how will this look in your calculator? We're going to say 1.53 and then that button, which means to the power of, and then parentheses, and then 1 divided by 12, close the parentheses. And then what do you get? So we get 1.036074, and that number keeps going. So when we round this to the nearest 2 decimal places, 1.0 what will it be? Well, this 6 is going to make the 3 turn into a 4. And as you can see, that is exactly what we should have gotten, 1.04. So when they say the number of branches grows by a factor of how much, we now know that every month, right, every 1/12 of a year, the number of branches grows by a factor of 1.04, which also corresponds to our b to the power of f of t. So our answer is 1.04 when we round to the nearest hundredth. If you want to make it look just like the previous problem, you could always just cross out this month and instead think of it as 1/12 of a year. But that should be plenty clear by now. So really the key for today's lesson is to make sure that all of the units for time in our problem, like in this case, we had months. In the case up here, we had seconds, are the same as the units for time that they tell us are being used, such as in this case, years, in the original model. And how do you make sure of that? Well, you convert the units. Congratulations, because you also just practiced some skills that are very useful for physics. See you next time. Hey.